Ok, on va démarrer. So first, do you have any question about last week's class? There were a lot of definition, but we will come back to it when needed, so don't worry. So as you know, we will start 1 hour talking and introducing the centrality measures in networks, and then you will practice, and here you have some experiments to do. So the idea is that you take this piece of paper in the second hour, and you try to do it, and I help you to answer your questions. Okay, so let's try with the centrality, talking about centrality. So centrality is a term which is used to describe, to measure some kind of importance, but also some property of the node. And the term is not really good because it's not necessarily being central in the network. Okay, so centrality is more than that. It's more, are you important on? Yes. Yes, sure. Is good? Okay. So some centralities have a straightforward interpretation. We will see that many of them we can really understand what they measure. So in that case, it helps you to understand what is the position of the node in the network. Some of them might be more difficult, but it's not necessarily a problem because in that case, you can, for instance, with machine learnings, you can use them as node features to try to predict something, for instance, to predict something that will happen with this node. We will see that much later in the course. So the first type of centrality, we already introduced it, it's a degree centrality. So you remember what is a degree, number of neighbors, or you can also have the number of in degree, out degree. So just a number of neighbors, and often actually it's already enough to identify some important nodes in your network. So for instance, if you take Twitter as an example, the people who have a very high in degree, they are very popular, so they are very important people in the network. So the degree usually is already enough to identify some important nodes relatively to some aspect. Popularity in Twitter. Same in airports, for instance. Major airports, they probably have a lot of connections to other airports. So if you have a high degree in the network of connection between airports, you're a large and important airport. But it's not always the case. Here are some examples. For instance, so if you look at out degree in Twitter, so Twitter account that follow many people, for instance, or in Facebook, if you have the account with many friends, usually they are just spam. Another example is Wikipedia. In Wikipedia, if you have, so if you consider a network in which each page in Wikipedia is a node and links correspond to hyperlinks, then if you have a very high degree, probably you've just a list of reference. So you have a page which lists everything that happened in 2011, and it has a lot of references. It doesn't mean that this page is really contains some really useful and interesting information. It just means that it has a lot of links. So it's a good proxy. So often it's the first thing we compute, but it's not enough in every case, obviously. Second one, we already introduced it also, is the clustering coefficient. So this one, we have already introduced it as the density of the neighborhood. I remember you. So for instance, in this case, the blue node has 3 neighbors. If they are all, so if I take the subgraph composed of these 3 neighbors, they are all connected. So it's 1. If none of them are connected, then the clustering coefficient is 0. And in this case, you see that among the 3 neighbors, there are 3 possible edges. Only 1 exists, so the clustering coefficient is 1/3. Just a reminder. But this means that you need to be careful because it doesn't really make sense to rank nodes according to clustering coefficient. If you rank them according to degree, you will have the higher degree on the top, probably the most important, and at the bottom you will have some nodes with 0 or only 1 connections. But here, the degree with a value clustering coefficient of 1, maximal value, they are probably just nodes with 2 connections, and these 2 connections are connected together. So it's not a good proxy of that. But so if you want to interpret it, you can use it as a proxy for communities belonging. So if you belong to a single group, you have a high clustering coefficient. If you belong to several groups, then you will have a lower clustering coefficient. So one thing you can do, for instance, is just to limit yourself to nodes that have at least 20 neighbors or at least 100 neighbors, depending on your network. So you select some nodes which are of the same size, basically, in terms of neighbors, and you can compare their clustering coefficient. A variant of this is the clustering coefficient for links. So it's computed in the same way, not exactly in the same way, but it's the same kind of interpretation. So you have it as definition here. You can interpret it as the Jacquard coefficient of the neighborhood, basically excluding the original nodes. Let's see it with an example. It's easier to understand. You want to compute the link clustering coefficients of this link, the link between I and J. So what you do is that you count the number of common neighbors between the extremities of the edge. So here there are 3 common neighbors, right? 1, 2, 3. These 3 nodes are neighbors of both I and J. And then, so this is the intersection between the neighborhoods. And then you count how many nodes in total there are in the neighborhoods of U and V. So you're counting 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so it's the value is the number of common neighbors divided by the total number of neighbors, excluding themselves. That's where the -2 comes from. So we can say that a link which has a high value will be integrative. So it's kind of bringing nodes together, and otherwise, if it has a low value, then it's dispersive, which means that okay, maybe it's in the middle of different parts of the network. Okay. So these were already familiar, and now I will introduce some new ideas, which are fairness, closeness, and harmonic centrality. The 3 of them are quite related. So the first one is so fairness and closeness, and must basically measure how close the node is to all other nodes. So it's the same idea as the center of a circle, right? So you have your circle here, and this the center, its property is that it's the closest to all the points of the nodes of the circle. So if I look at a point which is here, it will be very close to this part of the circle, but it will be very far from this part, right? It's the diameter. But the center is a distance as most r from any other point in the circle, so it's the closest to all the other points. So if you look at how the closeness looks in a network which looks a little bit like a grid, well, you see that you have this shape that the most important node in terms of closeness will be kind of in the center, and then you have this pattern of having a value which is decreasing with the distance to this center of the network. So this one is really can be interpreted as a center. So yes.
How do we find the center? We measure all the distances.
Yeah, we'll define the definition. So here is the definition of this. So to understand it, we can define it. We can define first the farness. So the farness is very simple. It's the average distance to all the other nodes in the graph. So we have defined the distance before. It was the number of hops in the shortest path between two nodes, right? So you know that there is a unique distance between any two pair of nodes. And so this is the distance. And so the farness is the sum of the distance to all the other nodes, right? And it's the average. So very simple. And since in the other centralities, we usually tend to like when you have a high score for the most central, right? But while in the farness, it's the contrary. If you have a high value, it means that you're far from everyone, so you're not in the center. So that's why we prefer to use, instead of the farness, the closeness. And the closeness is just the inverse of the farness. So basically, you compute your sum of distance to everyone, and then you take the degree and you divide by this value. So here is an example. You have this network. It has 6 and 6, 12 nodes. And so if I want to compute the closeness, I see that here I have 12 minus 1. And below, I will count the distance to all the other nodes. So I see that from this node, I have 3 nodes at distance 1. So it's 3 times 1. I have 7 nodes at distance 2. So this one, all these ones are distance 2 because they are directly linked to this one. So it's 1, 2, 3, 4, 5, and then 6 and 7. So you have 7 nodes at distance 2. And then you have 1 node at distance 3, which is this one. So this is how you compute it, and you get a value. And so if you if you compute this value for all the nodes, you will find the highest one, so the most central node. Okay. So if the value is 1, it means that all the nodes are at distance 1. And here you have a pictures of what it looks like in a real network. So this is an urban network of Amsterdam, where the connection corresponds to roads, bridges, and so on, where you can cross by foot of a vehicle, let's say. And you see that you really have this pattern where the most, the node with the highest closeness, they are kind of in the city center, while in the periphery, you have lower values. Okay? So we immediately see that it's a good way to identify some central area in your network. The harmonic centrality is a variant of the closeness. It's really the same interpretation, but it just solves a little problem of the closeness, which is that you cannot measure the closeness if your network is disconnected. It means if there are 2 nodes for which there is no path between them. Okay? They are really in separate components. So in this case, what happened is that since you're computing a sum of distance, if you have one of the distance which is infinite or not defined, then you cannot compute the value. So in the harmonic centrality, well, it's the harmonic means. So you are actually computing the sum of for every pair of every other node. You compute this value, so the inverse of the distance, and you define that if the nodes are not connected, then the distance is infinite. So you get 0 on this value. So you're computing a sum where there can be some 0 in the sum. And then you take the average, and it's the same. So it's just the average of the inverse of distance. So very quickly, how to if you check what on a simple example, you see that it's just like before, 12 minus 1, and then you have 3 nodes at distance 1. You have 7 nodes at distance 2, and you have 1 node at distance 3, and you see that you get a score which is different. But actually, we will see on examples that it's very, very similar. But it solves this problem. disconnected parts. Okay, another centrality, the cat centrality. It's based a little bit on a similar idea, so this idea of being close to many nodes, but in this point, it's really, so we will see the difference. It's set to measure the influence potential of a node. So how much, so for instance, if this node wants to, I don't know, diffuse an ID, how much, how many other nodes it can influence with this ID. Okay, that's why it was introduced. Well, after that we can discuss exactly what it means, but so it's defined on this way, and I will detail the formula. So the cat centrality is defined by this formula, which is doing the sum for all distances as long as possible. So we will make a computation for all nodes at distance 1, then a different one for all nodes at distance 2, then again at distance 3, and so on and so forth. So for a given distance, we compute the sum for every other node of a parameter which decreases at each iteration, so at each distance. And you see that it's a parameter between 0 and 1. So when you take the power, it's decreasing very quickly. And we take the number of different paths from I to j. So this is something that you have in the cheat sheets that I provided, but I have no time to explain it last time, so I will just introduce it every time we need something like that. The graph can be represented as an agency matrix. And so this means that the node 1 is connected to the node 2, so there is a 1. There is a 0 because 1 is not connected to 3. And if you take the square of this matrix, it gives you on each position ij the number of paths of distance 2 in this case. So there are two paths of distance 2 between node 1 and node 2 in this case. And if I take if I again multiply this by a, so a to the cube, then I will have the number of walks of distance 3. Okay, and so on and so forth. So this is what I'm doing here. I'm multiplying the matrix, so I get the number of walk of a given distance, of distance k, and I'm just counting how many there are between nodes I and j. So in the end, this ends up to summing the paths to all the other nodes at each distance multiplied by a factor decreasing with distance. So basically, if you have many nodes at a close distance, your value will be high. And if you have to go far to reach many nodes, then your value will not be so high as if they were closer. Okay? Yes? What is alpha? Is a parameter. So you have to choose it between 0 and 1. And it tells you how much importance you give to the node according to their distance. So for instance, if you choose 1, you say that if you are distance 1, 2, 3, 4, or 5, it's as important. It doesn't import if you can reach quickly or not. If you choose an alpha which is very small, it means that the ones which are very close, they will count a lot. But if they are, I don't know, a distance of 3 away, they are too far. And you don't count them. Yes?
Explain why when you put the matrix of the 4 2 you get the number of passes.
So actually, it's just when you multiply your matrix, you're taking all the links. So a row of the matrix corresponds to all the nodes you're connected to. So it's actually your neighborhood. And when you're taking the column, you're counting how many neighbors for instance, this is for node 1. It's connected to 3 nodes, this one, and this one. Okay, and if I take the last one, you see that this is the row of its neighborhood. And when I multiply the two, I will get, for each value here, the number of paths, how to say, the number of paths to all the other nodes, and then that come back to myself. So when you multiply, it just, it's just as if you were counting basically the work, the number of work. I don't know if there is a simpler way to explain it. Let me think a little. I don't find an intuitive way to explain it right now, so I will think of it maybe and add some intuitive explanation. Okay. Any other question? Other question on cat centrality? So you see that already it's a little bit harder to understand what's going on with this core, but still we get a sense of what it means. If you can reach many nodes in a few hops, then you consider it important. Let's move to the betweenness centrality. So this one is really one of the most important, most famous one. It's called centralité d'intermédiarité in French. Really important in both in social networks and when analyzing infrastructure or such networks. We will see why. It's quite simple to understand. Actually, it's the betweenness of a node is the fraction of all the shortest paths between all the other nodes that go through this node. So let's see it with a picture. I will come back to the formula later, but first let's look at the picture. It's easier to understand. So we want to compute the betweenness of node U. Okay. So we will look at the shortest path between all the pairs of nodes in the network. So for instance, what is the shortest path between this node and this one? It's going like this, okay? It's not going through U. Then what is the shortest path between, I don't know, this node and this one? So the shortest path is this. So it means that this shortest path is going through U. And so what you're doing is that you're counting all the shortest paths in the network. How many of them are they? So it's simple. The number of shortest paths is the numbers of different pairs of nodes. So it's defined as so in a directed network, it's the number of node minus one because we exclude U. So it's the total number of nodes in the network times the number of node minus one. So this is just the number of pairs there are in the network. And then we count the number of these shortest paths that go through U. So for instance, let's compute it for U. We see that from these nodes, all these nodes, if I want to go to reach these nodes, obviously I have to go through U. Okay? So I have 1, 2, 3, 4, 5 nodes here, 6 nodes here. So there are 5 times 6 pairs of nodes for which the shortest path is going through U. Okay? It's good. From all the paths here to all the paths, from the nodes here to the node here, I have to go through U. So it's 5 times 6. This is the number of paths going through U. Then, what are the other paths that have to, the other shortest paths that has to go through U? There is one here, right? If I want to go from this node to this node, I have to go by U. So this is 5 times 6 plus 1. And then that's what is written here. Actually, the problem is that sometimes you have several shortest path between two nodes. And one example is between this node and this node. There are two paths of length 3. There is this one and this one. Okay, so I count how many shortest paths there are, different ones. There are two different shortest paths, and one of them is going through U. So I take the number of shortest paths going through U divided by the number of shortest paths between these two nodes. So I take 1/2. Okay, so from this one to this one. And again, the same problem arises between this node and this node. Okay, one is going through U, the other is not going through U. So this is how I count the betweenness. So there is a 2 here because it's directed, while in this formula it's undirected, but it's not a big change. Just because of the symmetry, UV and VU is the same. So in the end, I have counted all the shortest paths that go through a node U, and the number of pairs of nodes, so possible maximum number of shortest paths there could be, and this gives me the score. Okay, simple. And one problem we see is that you need to find all the shortest paths to be able to compute this score. So it can be very long to find all the shortest paths, but there are actually efficient algorithms. So for instance, you can see it maybe in one of the tutorials. I will propose to code it if you have the time. The Floyd-Warshall algorithm, which is in a complexity in cubic with the number of nodes. So it's costly, but if your network is not too big, it can work. And there are much faster approximate computation where you give a limit in the number of the longest distance that you accept to use, and you get some approximate computation of the betweenness. So we can compute the betweenness on very large graph in an approximated way. So here is a figure of what it looks like on some node. So on this one, which looks a little bit like this circular grid like before. So the blue are higher scores, and you see that the nodes which are kind of in the middle, they have the highest value, like before. Why? Because it's a little bit like a circle. So if you want to go from a node at the periphery and you want to reach another one, you need to go through the center to reach it quickly. So in this kind of networks, it won't change much. But here is an example where it's changed a lot. You see, compared with the closeness, it's not at all the city center, which is in red, the highest value, but it seems to be some areas in the city. So knowing this represents Amsterdam, do you have an idea of what will be the highest value of betweenness? So this is pattern of streets, right? So each node corresponds to a particular part of road between two intersections. Do you have any idea what is essential in what type of things you need to cross often in Amsterdam? Yes, the bridges. Yes, because you have canals, so very often you cannot cross easily from one street to another, but you have to go through a bridge. So the bridges will tend to have high value of betweenness. And so the interpretation of the betweenness is that it's measure. I don't know if I say it. I don't say it maybe here. I don't know. Well, it's measure the bridgeness. Yeah, it was my first sentence here. The betweenness measure kind of the bridgeness of a node. So how much, in particular, if you remove this node, it will tend to disconnect the graph or make the communication harder in the network. So a little game. So there is the edge betweenness also, which is computed exactly the same way. You count the shortest path, and you count how many of them are going through a particular edge. So little game, can you guess on this rail network what is the edge of largest betweenness? Do you have an idea? Sorry? So probably it has a high value because it seems to be in the center right there, but there is probably a link with a higher betweenness. It's kind of special. Which one? Belgium and Luxembourg. Yeah, probably also we are between Spain, so we are kind of also in the center. But there is one edge which is not so much in the center, but it has a particular position. Belgium? Yeah, it's the tunnel, the tunnel which is going between France and England. Because if you remove this single connection, you completely disconnect one part of the network from the rest. While if you disconnect some part of the connection between Spain and France, you can still cross by other ones. So you will just add maybe one hop to several transfer. But if you stop the connection here, well, it's the end. You cannot go by train to England. Okay. Any question about these centralities already? No. I will just make a short break. No question? So let's start the last type of centralities, which are based on recursive definitions of centrality. So they are a little bit harder to grasp, but very interesting. So we want to define the fact of being important as something which is recursive because you're important if you're connected to important nodes. Okay, so you need to be connected to many nodes, okay, but these nodes need also to be important. If I'm connected to many nodes, but all of them are connected to no one else, maybe I'm not that important. For instance, it could be a good way to identify fake accounts, right? Okay, I can maybe create an account with many friends, but if all these friends are also fake accounts, well, maybe they are connected to no one, and I'm not that important. So there are several centralities based on this idea, and we will see two of them, eigenvector and PageRank. So we would like, so what does it mean to have a recursive centrality definition? It means that each node has a score with centrality, and we want that if every node sends its score to the neighbors, and then each node it sums all the scores received, then we get we stay on the same value. That's how it is defined. So this is what is written in this equation. It's some recursive process, so iterative process. So we want the centrality of node u at t+1 to be the sum for all the neighbors of u. So if it's directed, we take the in degree, what I receive, but otherwise, if it's not directed, all the nodes. So the sum for all the neighbors of u of their centralities at time t. Okay, so it's iterative. I want my score to be the sum of the score of my neighbors. And I just normalize this to avoid increasing every time. I will normalize it so that I get a constant value. And so one way to solve this problem is actually kind of magic, is that, okay, you want to reach this stable point where when I send to my neighbors, I still have the sum of what I received is still the same. Well, you can solve it by just putting some random values on your node. So on your node, you put some random values, whatever. You apply the mechanism. So everyone sends to the neighbors sum what they receive. they have a new value, and you start again. And if you do that long enough, you will reach after some times a stable point. And this stable point will be what you searching for, because it's a definition. You're something where when you reach it, you still stay on the same values forever. So why does, so it means that this algorithm converge. Why does it converge? Well, actually, it's said by Perron-Frobenius theorem, and it's true if the graph is undirected with a single connected component. So this is what eigenvector centrality is, and it's called this way because it's very simply described in terms of eigenvectors. So for those who don't know what an eigenvector is, just don't really care about that. But if you know, then it's very simple to understand. You have a couple. So you know that we define a couple between eigenvector and eigenvalue by the following relation. And if you consider that X is actually a column vector of size n, so the number of nodes, then you consider that this vector corresponds to the centralities of the node, right? The first value corresponds to the centrality of node 1, the second to centrality of node 2, and so on and so forth. So when you do this operation, what you're doing is that you're actually propagating the values to the neighbors. And what you're saying is that if you propagate this value to the neighbors, then you want to still have the same values to a normalization factor. Okay, so this is exactly what we have defined. And what Perron-Frobenius algorithm says is that the power method will always converge to the leading eigenvector, so the eigenvector associated with the highest eigenvalue. Okay, so I propose in one of the experiments to check this on a network. And yes, so that's why it's called the eigenvector centrality, because it's very simply computed in terms of eigenvectors. Yes? Yes, A is the adjacency matrix. So very good, very well. It's very clearly mathematically defined, and you can understand it relatively easily. There is just some problems. So the first one is when you start to work with a directed network. So if your network is directed, you have two sets of eigenvectors. So you have two leading eigenvectors. So you have to use, so one solution is to use the right eigenvectors. So, okay, so this is a minor problem. But then you get to a major problem, which is the problem of source node in directed network. So what is a source node? It's in my definition in the cheat sheets, but the source node corresponds to a node which has no incoming edges, like this one, right? They are outgoing, but not ingoing. And if you remember the power method, you know that okay, I initialize this node with a random value at first to start. And then after the first step, its value will be the sum of all the value received from the neighbors. But in this case, since there is no incoming edges, the value at time t+1 will be 0. I received nothing, I sum nothing, so my value is nothing. So the value is 0. But the problem, so okay, you could say that's a problem with this source node, but maybe this source node, by definition, they are not important, so just assign a score of 0 and it's fine. But the problem is that it's a recursive process. And now, if you look in this small example at node B, you see that node B, it has incoming edges, but it has only one. And these incoming edges come from A. So at step 2, what happens is that A is now sending 0 to this neighbor. So B is making the sum of all the incoming values. So 0 plus 0 equals 0. So now B also is 0. And then on step 3, you see that this node actually has 2 incoming edges, but they come from A and B. So now you're doing the sum of 0 plus 0, and it's again 0. And you see that these zeros, in the end, they can propagate to the whole network. And so you get all the values equals to 0, and it's not interesting anymore. So that's the problem with the eigenvector centrality. You need to have an undirected network, or if it's directed, it needs to have some properties like you can compute it only in a strongly connected component. So if you remember the definition, this means that between any pair of nodes of the strongly connected components, there is a path following the direction of edges. Okay? So if there is a path between all the nodes following the direction of edges, there is no source by definition. And the problem is that the network with source are quite common. For instance, a good example is a citation network in which your nodes are papers and edges correspond to citation. Well, the latest papers, by definition, they cannot be cited by anyone. So we have a source degree of 0. So if you take the latest papers, they will all propagate 0 to papers published last year, that will transmit 0 to papers published the year before, and so on and so forth, and you end up with only zeros. Okay, so this is a problem with eigenvector centrality. And so a solution was proposed using an algorithm called PageRank. So this is the paper in which PageRank was proposed, right? It's a paper published in 1998 in the World Wide Web Conference, famous conference in computer science. And if you look at the name of the authors, Sergey Brin and Lawrence Page, maybe you know them already. So do you know who they are? Do you know who they are? They are actually the guys who founded Google. Okay, so they are they're both at Google. They are the guy who created Google. And they were actually working at Stanford at that time. So this is, now if I show you the abstract, you see that in this paper, they wrote in this paper, we present to Google a prototype of a large-scale search engine which makes heavy use of the structure present in hypertext. Okay, so actually this is the paper that made Google possible. Google is actually just the implementation of this algorithm. Google, well, the search engine, not all the other stuff they have done after that. So actually, this paper is quite fun to read. So I was reading it, and so first I explain why they chose Google. But this, maybe you already know it. It's the common spelling of Google, this number, and it corresponds to the building a large-scale search. But what is more fun is another extract of the paper. So I will read it for you. Up until now, most search engine development has gone on at companies with little publication of technical details. This causes search engine technology to remain largely a black art and to be advertising oriented. With Google, we have a strong goal to push more development and understanding into the academic realm. So very good. They had very, how to say, angelic ideas. And they even say at some point, we expect that advertising-funded search engines will be inherently biased toward the advertisers and away from the need of the consumers. So you see that in this paper, they were still not thinking about building a company. They were really trying to propose something really new and open for everyone. But at that time, they were PhD students at Stanford, so basically, it's normal. Okay, so what is PageRank? How is it defined? It's basically eigenvector centralities with some minor changes. One is so we have this problem with source node. For example, the solution is simple. You just add a small value to every node at each step. Okay, very simple. The problem was that sometimes we have 0. So what we do is that we take a very small value and we add it every time. At every step. Okay, simple. And another problem I observed is that node with high centralities, we are giving very high centralities to all the neighbors. So let's say that one web page, for instance, is very, very important. We give it a very high centrality. And then let's say that it's connected to, it's making links. For instance, it's a let's say that it's for instance, what before Google, before search engines, to find a web page on the internet, you are using some collections of web pages. You have websites with categories, and you could go in category, I don't know, animals, and in animals you had categories cat, and in cat you had links with thousands of pages talking about cats, right? And the problem is that a web page like this is obviously very, very important in the World Wide Web, but it has many, many connections. So if it gives all its importance to all the neighbors, you will end up with something weird. So what they propose is that you actually divide your score to when you send it to the neighbors. So this is the minor change between the eigenvalue centrality, as we have seen it before, and the PageRank centrality, in which you divide this value by value out degree, and you add this constant. Okay, as I said, a small number. And there is this alpha here, which is just to, so we usually put beta at 1 for technical reasons. And then with alpha, you can control what is most important. Is it this value that we add every time, or is it what you compute? So alpha is just this parameter. So in the original Google, it was PageRank, it was set at this value, for instance, by default. It has also a matrix interpretation, which is actually called even now in the literature the Google matrix. The idea is that you normalize your matrix, you create a matrix S, which is normalized by column. So now the one, if you have 2 ones in a column, it becomes 1/2 and 1/2. If you have 3 values, it becomes 1/3 every of them, or 1/5 if you have everything like this. And then what you do is that you add to each cell, you add some constant, right? So there is 0.03 here that we add to all of them. And then you multiply by this alpha, your parameter, 0.85 in what I said before. So this is defined in this way based on the adjacency matrix. And this gives you the Google matrix. And from this Google matrix, just as before, you can compute your eigenvectors and eigenvalues, and the leading eigenvector will give you the PageRank score. Okay. And there is another way to interpret this PageRank, which is also quite maybe can help to understand what's going on. It's that actually when you normalize by column, what you get is a random walk matrix. So it corresponds to what is so how a random walk choose to move in a network. So what is a random walk? So it's I have some I define it in the cheat sheet, so you can check it what I provided in the first class. But basically, to make you understand what is going on with PageRank with a random walk. Random walk is that you start on you start on one node chosen as random in your network. Okay? So the random walker starts from this node and move randomly by picking one of the outgoing edges randomly. So if you're on a node that has 3 connections, I will pick one of the 3 with the same probability of 1/3. So every time I'm on a node, I'm choosing one of the neighbors and I move to this node. And then I continue. I move to the next, one of the other neighbors, and then again to one of the other neighbors, and so on and so forth. So this is called the random walk. And the idea is that, so it's a Markov process. You just don't remember where you're coming from. You just know that you're on this node and you see the connection and you choose one randomly. And you do this forever. You do this for an infinite number of times. So it doesn't really, it does not depend on where you started, because you do it an infinite number of times. And what introduced the constant value and the alpha, it tells you that you have a probability alpha. Well, with probability alpha, you will do what I've described before until now. but with probability 1 minus alpha, you will just jump randomly to another node on the network, whatever node. So this explains this small constant, this small probability you add the small score that you add to each node is the probability that you jumped randomly to this node. And so it tells you. I did not. No. Okay. So it tells you that. So this tells you that if your alpha is big, you will tend to mostly follow the normal process. If your alpha is smaller, then you will tend more frequently to jump to random nodes. And so the PageRank score can be interpreted as the probability that this random walk at a particular point in time after an step is on a particular node. Okay, so you have this process, you're moving from node to node. Sometimes with a certain probability, you're jumping to other nodes, and then you move around this node, then you jump to another, you move around, you jump, and so on and so forth. And the PageRank score can be interpreted as the probability that you are, so the PageRank of node U is the probability that you are at node U following this process. Okay? So you see that if you have many incoming edges, there is a high probability that the worker is on you, because it can come to you from many nodes. But on top of that, if you have many incoming edges, but the nodes that are pointing towards you, they also have many incoming edges, then you're even more important because you're kind of attracting everything happening at a far distance because many nodes point to nodes that point to you, so you're aggregating all of them. So that's the idea of PageRank. So actually, how do Google use PageRank? It's very simple. First, they compute PageRank of the whole network. So they do that using actually the power method because it's convenient. It can be also updated easily. So they compute this PageRank using the power method for scalability, and then they create just a subgraph of what you're searching for. So if you enter, I don't know, network science, then they filter all the pages that contain the word network and science, and they give you as first result the highest page, and then second the website with the second highest PageRank, and so on and so forth. So this is as simple as that. So well, it was as simple as that because in the beginning, the first Google was really doing exactly that. But so you could even browse for a page and ask to Google what is the PageRank of this page, and you could know what was your PageRank score. But the problem with that was that since you know how it works, you can more easily try to trick it. So you can try to create fake pages that point towards you and try to bias the results so that your page arrives first. So now we don't know what is exactly how Google works, the Google search engine works exactly, because it's probably much more complicated than that. Yes?
Actually, the off is finding the best subgraph that's actually.
Well, usually the way this search engine works is very simple. You just filter all the web pages that contain what you're searching for. So if I search network and science, they remove all the pages where there is not both network and science. Okay, so you just keep only the pages that have the word you're searching for, and you rank them based on that score. So you don't even need to compute the subgraph. So there is a personalized PageRank, which is actually looking around some parts, but in the first version of Google, there is not even, you compute your PageRank one and only one time on the whole network, and then you just, so I can, if I just search, let's say I search with no topic, I ask, give me the most popular pages, it will give me first the page with the highest page. But of course, if I search with the word network, well, maybe the most popular page does not contain the word network, so you remove it, and then you provide me with only the page that contains network and that has the highest value. Okay. So probably now they use something much more complicated in which they maybe change their score relating, but I mean, when you get the result from Google, it's obtained in a fraction of a second. They are not computing something for the first time. Everything is already pre-computed. So the score of the nodes is already computed when you're doing your research. Yes.
The page that is on search of, not like you have a page. Then when you search, you get
yeah, so this is true, but it's actually because as I said, now it's a little bit more complicated than that. But it's not. So the ranking is not. So it's not the page rank which is updated. Is that the ranking depends on both page rank and something else. So okay, it's page rank, and then I will also take into account what you like, and I will update your results based on that and the order. But it's not recomputing something on billions of web pages every time you're doing a research. Okay. So as I was saying, yeah, so probably they changed the way it works, but we don't really know because as they wrote in the paper, most search engine development has gone on at companies with little publication of technical details. So it remains largely a black art, and yeah, it's what's happening now. Many other centralities have been proposed in the literature, probably hundreds of centralities, because anyone can just get a good, nice idea and write a paper about that and show that it has some interesting properties. So there are many, many centralities. The goal is not to introduce you to everything, and I don't know everything, of course. The one I presented are the most popular ones. So if you use one of these ones, everyone in the network science community know them, so you can use it without explaining why you're using them. I'm using this betweenness because I want to measure what's going on. I would want to find some bridge in the network, for instance. But you can use them otherwise as supervised tool. So this, you will see it at the end of the class, doing some machine learning. You can use them as features. So I compute, I don't know, 20 different centralities. And then let's say I want to discover important nodes in my network. I will train an algorithm to take these 20 values and from it tell me the importance of the node corresponding to what I'm searching for. So for instance, I don't know, I can on Twitter, I'm not interested in the superstar, but I'm interested in people who are a little bit bridge between different social communities and that are influencers, but not so much. I don't know, maybe some kind of people who are, I don't know, for instance, journalists. I would like to recognize journalists. And what I will do is that I will compute all these centralities for all the nodes. And then I will take these centralities and I will show 100 journalists and tell train the algorithm to recognize journalists based on these 20 values. And then I will ask the algorithm to giving these 20 values for this node, will you think it's a journalist or not? Okay, so in this case, it's kind of using machine learning, but using as input centralities. Even if you don't really know what they mean, it's not a problem because maybe one of them capture a little bit the richness, another one capture the close neighbors, and so on and so forth. And from all these elements, you can combine a good predictor. Another little game. Here are all the centralities I explained. And here are networks. Can you guess which is which? So don't check the answer, which is on the next slide, if you have the computer, but just try to think a little. Of course, it's very difficult. Probably you won't succeed, but you can find some elements, especially if you don't see where the white. Okay, if you don't see anything, it's that it's white. White means very low value. And if it's red, it means that the value is high. So think a minute, and probably you can say that some networks some of them are not something, or some of them are good candidates. Any insights? Yeah.
Say that F or G has F, see that group our left and bottom are same color, and you can see that more or less filled out.
Yeah, it's a good guess. I think degree is relatively easy to identify. Probably the betweenness, not too hard to identify, and the clustering coefficient is quite special also. You have good guesses for one of those? You can say, you can be wrong, there's no problem. Yes?
I just say B. You see, different well, match objects.
For the bottom right one, if this one is white, it has two, while the middle one, the left, and the two.
Another hint is that these two seems very similar. So maybe we have seen also some scores that are very similar. So is it compatible with this theory? What about this one? It's kind of special because the nodes that are important, right, the high degree, they seem to have very low values.
It's like the same as the get turnarounds, which is more.
So I will say not because, for instance, this node seems to be important, right? It's still connecting this part to this part. So probably not between us.
Yes, would be like A or B, or the single node is quite important.
Yeah, good theory. Any other ideas? No? Getting tired? So this one, you can, so the problem is that we don't see very well all the connections, but if you look at this, you see that there is something special about this part of the graph, that there are no connections. So if you know that there are no connections here between the white, what do you think about that? So this part of the graph is a tree. It means that there are no connection. You don't have connection between the branch of this part. So, and here it has only zeros. Only all the values are very small. Yes. Okay. So it means that there is a probability to jump to this one, but it's true that we don't really see the difference for the other one, so it's difficult with the small value to get something. Yes. Yes, this is very likely because we see that these they have a value which is very high, right? Because they have few connections and there are triangles. All the other ones they don't have triangles. So very probably this is the clustering coefficient. Yes? So E could be betweenness because you have, some of the interconnection between them which are very high. And the difference with this one is maybe if you try to skimmed a little to look not clearly, do you maybe see some kind of pattern in these two ones? Yeah, there is kind of this circle shape I was describing for the closeness. So they are not distinguishable, but one of them is probably the closeness, and the other one is probably the harmonic centrality. Okay, so we are not so bad. Do you have any other guess? So the order is not the same, but so the first two one were closeness and harmonic. Then you have the clustering coefficient, which is only these three house colors. The degree, well, degree is easy to interpret. The betweenness was, in fact, yes, this one with very high value also in this one, which connects all the parts. But these nodes, they have also not so bad values. Even this one, which has only two connections, but since it's on the way between this part of the graph and this part of the graph, it has a high betweenness, which is quite rare because in most of the other metrics, it has a small value because it has only two connections. So cat centrality is a little harder to interpret, to discover, but the idea is that you kind of also in the center and you can access many nodes quickly. So actually this node can access a little bit all the network, not too badly, so it has a good value. But also this one has a good value because it can access to all these nodes very easily. So that's good. And these ones are not too bad because they are in the middle also of something, of a portion of the graph. So well, it's very hard to recognize, but that's the idea. Eigenvector centrality has this something that we observe quite often, is that there is kind of something that we call a rich club phenomenon, like a group of nodes that attract all to themselves. This part of the graph seems to attract most of the high values because they kind of diffuse their importance to the other ones, and they attract most of the values to themselves. And the page rank is this one, in which you see that well, important nodes tend to have many also connection, other pages linking to them. Like this page is let's say at the top of a hierarchy of links. Any comment or question on this? No. Another one, each easier. Knowing what I've explained, can you guess between four that are easy to recognize? Well, not that simple, but P closeness. Yes. A probably the degree. Okay. Yeah, with what I just explained, this rich club. Yeah. Maybe it does not make so much sense. And the other one, by definition, is betweenness, where we see that some nodes apparently they are in between parts, right? They kind of play the role of bridge between maybe this part of the graph and this part of the graph. So yes, I guess you're right. A is degree, B is closeness, C is betweenness, and D is eigenvector centrality. Okay, so we mostly understand what these centralities measure. Just a little caveats, maybe. Sometimes some of them are based on some predefined idea of what's going on the network. In particular, a good example is the betweenness. So the betweenness is counting the shortest path, right? Counting how many of the shortest paths are going through you. But if for some reason in your network information does not flow to shortest path, maybe the information is just going randomly in the network, or it can take shortcuts or whatever, then your bit centrality maybe is not adapted to measure what you think you should measure, because you're just counting shortest path, and if the shortest path does not make sense in your network, then it's not that useful. And that's all. I don't know why I have it. This, I thought I removed it. Okay. So this is the end of this part of the class. So I propose that you take a 5-minute break, maybe if you need. And after that, you take one of those and you try to experiment with centralities. And of course, I'm here to help you on technical aspects. Of course, you have this on the web page. If you don't need a piece of paper, you have it on the web page. And
sur la page de la classe les networks.
ah oui, j'ai oublié les lettres. C'est vrai. Je vais mettre les liens. Ta, ta, ta.
Les graphes available sur la page iPad.
Je suis en train de les mettre.
Ouais, d'accord.
Et là, normalement, il devrait y être sur le... Ouais, ils y sont sous les cours. Normalement, j'ai rajouté 2. Je suis en train de remettre un 3e. You see our centrality.